Hello students, welcome to EPG Pathshala. I am Dr. Manjula Sharma from University of Delhi. Today we are going to talk about the module Electron Beam Interaction with Materials under the paper Measurements and Instrumentation. After completing this module, the students will be able to understand the specimen-electron beam interaction, the emission mechanism and characteristics of signal, additional signals in TEM, then the detectors, and towards the end, the common modes of operation of the TEM. In electron microscopy, electrons emitted from a source are accelerated by an applied voltage, which can vary from a few kilovolts for SEM to a few hundred or even thousand kilovolts for TEM. The high energy electrons are focused to a fine probe on the sample or the bulk or specially prepared thin samples. The interaction between high energy electrons and the atoms of the sample gives rise to a variety of signals. The detection and quantitative characterization of the signals form the basis of SEM and TEM. The dual nature of electrons offers unique opportunities for the study of samples. The wave behavior is utilized in the formation of images and diffraction patterns. The charged particle behavior results in strong interaction with the atoms of the sample, giving rise to information on the chemical composition of the sample. Thus, it is possible to concentrate on a small region of the sample, typically from micrometer level to downwards, and obtain information on microstructure, crystallographic details, and chemical composition. The information available may broadly be summarized as morphology, that is, the size, shape, and distribution of phases, and their relationship to one another. High resolution images varying from micrometer to nanometer level. Then the crystallography, arrangement of atoms and their degree of order, detection of equilibrium and metastable precipitates, orientation relationship. All this can be found out. And the third, that is the composition, that is the elements present in the sample and their local variation, and provide a high resolution image. Students, figure 1 is an illustration of the various possibilities of electron optical techniques. Microstructural information can be obtained from the SEM, TEM, which includes STEM and HREM, the crystallographic details from the diffraction patterns, and chemical composition from analytical microscopy. In this module, we shall focus our attention on the signals arising from the interaction between the atoms of the specimen and the high energy electrons, their characteristics, information available, and the methods of detecting them. It will be emphasized that more than one signal may be used to obtain a specific information, say chemical composition. Students, now let us consider the specimen-electron beam interaction. The signals arising from the interaction of high electrons with the sample are schematically illustrated in figure 2. It shows the electron beam is impinging on the sample and several signals are arising from it, such as cathodoluminescence, Bremsstrahlung, characteristic X-rays, Auger electrons, secondary electrons, and backscattered electrons, which are useful for SEM. Also, there can be elastically scattered electrons and transmitted and inelastically scattered electrons, which are useful for TEM. Several signals, that is, the secondary, backscattered, and OJ electrons, X-rays, cathodoluminescence, are emitted on the incident side of the electron beam, that is, the top surface of the sample, while some are emitted on the exit side, that is, the bottom surface of the specimen. As electrons are absorbed easily in thick samples, that is, where the thickness is more than 1 micrometer, the transmitted electrons are observed only in thin samples. A study of the signals emitted on the top surface forms the basis of scanning electron microscopy, while transmitted electrons are used in the transmission electron microscopy. It may also be seen from the figure 3 that a considerable amount of heat is generated, which is to be transported away from the sample for prolonged observation. Specimen current is of interest in semiconducting materials. Typical depths in the sample from which these signals emerge are shown in figure 3. The penetration of electrons in the specimen is a function of the electron energy as well as the atomic number of the sample. The higher the energy of the electrons and the atomic number of the atoms in the sample, the greater is the penetration. It is clear from figure 3 that OJ electrons are emitted from regions very close to the surface, that is 0.5 to 5 nanometer. Secondary electrons from a slightly deeper region, that is around 10 nanometer, while backscattered electrons emerge from a region of 1 to 2 micrometers. Characteristic and continuous X-rays emerge from a nearly pear-shaped volume with dimensions of a few micrometers. Now, let us see the emission mechanism and characteristics of signals. The mechanism of emission of secondary, backscattered, and OJ electrons and X-rays, that is K and L, are shown in figure 5. Figure 5 shows the excitation of backscattered and the secondary electrons. Also, it shows the emission of OJ electrons, the X-rays in the L lines and the X-rays in the K lines. Secondary electrons are the loosely bound electrons near the surface of the sample, ejected by the incident high energy electrons. They have energy in the range 10 electron volt to 50 electron volt. Secondary electron yield increases with increasing tilt of the sample with respect to the electron beam direction and increases with decreasing energy. Backscattered electrons, or BSE, are those deflected by the nuclei of the atoms. They have energy in the range 100 eV to EP, that is the energy of the primary electrons. The lower energy electrons have obviously reacted with the sample before being ejected out of the sample and in the process lost a part of their original energy. They are referred to as high loss backscattered electrons. The term backscatter coefficient, or neta, refers to the ratio of the number of BSEs ejected to the total number of primary electrons. Neta increases with increase in the atomic number of the elements in the sample and with increasing tilt, and is marginally affected by the primary beam energy. The high energy primary electrons can cause ionization of the atom by ejecting one of the inner shell electrons, that is K, L or M. The ionized atom returns to the ground state when an electron from a higher level fills the hole in the inner shell caused by the ejected electron. The extra energy available is utilized for the release of an X-ray photon, that is KLM or characteristic X-ray, or to knock out an electron from an outer shell, that is Auger electron. Energy is specific to the element emitting X-rays. For example, aluminium K 1.48 keV. Energy generally lies in the range 1 keV to 10 keV for K radiation of common elements and L and M radiation for heavier elements. The energy E or wavelength lambda is characteristic of the element and the intensity is a measure of the concentration. This forms the basis for electron probe microanalysis (EPMA) and analytical electron microscopy, that is AEM. Also, the variation in the concentration of an element along a line or area can be measured, which is called as line or area mapping. Fluorescent yield omega is the ratio of the number of X-ray photons emitted to the total number of ionization caused. Suppose there are 1000 vacancies caused in the K shell and 300 K X-ray photons are emitted. The fluorescent yield of the K X-rays is 0.3. The variation of omega with atomic number is shown in figure 7. It is seen that for elements with atomic number less than 10, the fluorescent yield for K, L and M X-rays is negligible. Since X-ray and Auger electron emission are complementary processes, Auger electron yield is high for the low atomic number elements. This explains the common use of Auger electron spectroscopy for the study of light elements such as carbon, oxygen and nitrogen. The energy of the Auger electrons, that is from 10 eV to 2000 eV. Since these electrons are easily absorbed by the environment in the microscope, high vacuum conditions are necessary for characterization, a condition which is difficult to obtain in a conventional SEM. Since the Auger signal originates from the first few atom layers, in-depth profile of elemental distribution is possible by ion beam sputtering. Students, now let us study about the additional signals in TEM. As pointed out earlier, thin samples are required for study in the TEM. The high energy electrons will penetrate the thin samples and signals emerging from the exit side can be used for characterizing the sample. It may be noted that even in thin foils, all the signals mentioned so far with respect to the bulk sample will be present, but with reduced intensity. Elastically scattered and inelastically scattered electrons arising from thin foils are used to provide information on microstructure, crystallography and chemical composition. Elastically scattered electrons have energy equal to the primary electrons. They will be prominent when the specimens are very thin. They can be used for the formation of bright field and dark field images and diffraction patterns. Diffraction patterns provide useful information on crystallographic relationship, sample thickness, and chemical composition. In elastically scattered electrons are those which have interacted with the sample and in the process suffered energy loss. The analysis of plasmon peaks and ionization edge forming the basis of electron energy loss spectroscopy provides information on chemical composition and defined structure before the ionization edges on the nature of bonding. Students, now let's study about the detectors. The signals arising from the interaction of high energy electrons with the atoms of the sample are studied with a number of detectors, as is shown in table 2. The more commonly used ones are the scintillation photomultiplier or Everhart-Thornley, that is ET detector for SEs and BSEs. Solid state detectors for backscattered electrons and the energy dispersive and wavelength dispersive systems for X-rays. Now, let us see the classification of the detectors according to the signal they sense. For secondary electrons, the scintillator photomultiplier or Everhart-Thornley detectors are used. For backscattered electrons, Everhart-Thornley or solid-state detectors are used. For absorbed electrons, the detectors which are used are microampere meter. For X-rays, the energy dispersive and wavelength systems detectors are used. For OJ electrons, hemispherical cylindrical mirror spectrometer are used. For cathodoluminescence signals, the monochromator or photomultiplier with lens are utilized. For elastically scattered electrons, the aperture with scintillator or solid-state detectors are used. For inelastically scattered electrons, the scintillator and photomultiplier and solid-state detectors are used. The ET detector is schematically illustrated in figure 7. It is basically a scintillator photomultiplier system. The secondary electrons are first collected by attracting them towards an electrically biased grid at plus 400 volt to plus 500 volt and then further accelerated towards a phosphor or scintillator at about plus 2000 volts. The accelerated secondary electrons are now sufficiently energetic to cause the scintillator to emit flashes of light, that is CL, which are conducted to the photomultiplier outside the SEM column via a light pipe and a window in the wall of the specimen chamber. The amplified electrical output by the photomultiplier is displayed as a two-dimensional intensity distribution that can be viewed and photographed on an analog video display or subjected to analog to digital and displayed and saved as a digital image. The brightness of the signal depends on the number of secondary electrons reaching the detector. If the beam enters the sample perpendicular to the surface, then the activated region is uniform about the axis of the beam and a certain number of electrons escape from within the sample. As the angle of incidence increases, the escape distance of one side of the beam will decrease and more secondary electrons will be emitted. Thus, steep surfaces and edges tend to be brighter than flat surfaces, which results in images with a well-defined three-dimensional appearance. It is possible to obtain a resolution of less than 1 nanometers. The preferential collection of the SEs and BSEs can be achieved by varying the collector, that is the electrically biased grid voltage, when the voltage is plus 400 volts to plus 500 volts. Secondary electrons are preferentially attracted. If it is maintained at a negative value, that is minus 100 volts, secondary electrons are repelled and backscattered electrons are collected, as is shown in figure 8. The principle of the solid-state detectors is illustrated in figure 9. The high-energy backscattered electrons are incident on a semiconductor detector where they cause the formation of a number of electron-hole pairs depending on their energy. If electrodes are placed on opposite faces of the detector and a potential applied with an external circuit, the free electrons and holes flow in opposite directions, producing a current flow in the external circuit. This current can be amplified and used as a video signal. Background or dark current in the circuit, the flow of current even when no electrons strike the detector can be minimized by the use of a PN junction. The common modes of operation of the TM are bright field microscopy, dark field, and selected area diffraction. Electrons passing through a thin foil are diffracted from various planes, and the diffracted beams from a family of planes, that is H1K1L1 and H2K2L2 in figure 10, are focused in the back focal plane of the objective lens. Thus, a set of diffracted spots are formed on this plane. The formation of diffraction plane or pattern and intermediate image is shown in figure 11. A suitable aperture placed in the back focal plane of the objective lens can be used for the formation of bright and dark field images. If the aperture blocks the diffracted electrons but allows the directly transmitted electrons to form the final image, a bright field image is obtained. Dark field images can be formed either by moving the aperture so as to allow diffracted electrons at a particular angle to pass through the aperture, or by tilting the electron beam so that the diffracted electrons at a particular angle go through the optic axis, that is, one diffracted beam moves to the center, as is shown in figure 12. Figure 12 shows the imaging in the bright field mode, in the A portion, in the dark field mode with shift of objective aperture, and in C in the dark field mode with beam tilting. The basic diffraction pattern is formed in the back focal plane of the objective lens. This pattern can be observed by projecting the back focal plane of the objective lens onto the viewing screen. In this case, the intermediate lens is used as a long focal length lens by running it in reduced excitation. The use of the selector area or diffraction aperture at the intermediate image plane allows the selection of the area on the specimen from which the diffraction pattern is obtained. If the size of the intermediate aperture is d and the objective lens magnification is m, then d by m is the size of the selected area. It is necessary to ensure that the plane of the intermediate aperture coincides with that of the intermediate image. So students, let us summarize what we have learned in this module. We have learned about the specimen-electron beam interaction, the emission mechanism and characteristics of signals. We learned about the additional signals present in the TEM. Then we learned about the detectors and the common modes of operation of the TEM.